Okay, so welcome everyone. This week we have Zhang who will tell us about the coarse systems from dynamically convex.
Awesome. Thank you very much for the invitation. It's a pleasure to be back in Princeton. And so I want to talk about a recent result with J.Dardennes, V.Ramos and J.Zhang. And the general question we have in mind is roughly can be formulated as what is symplectic convexity? So what I mean by what is that, how does it come is that if you look in R2N, and then you have geometric convexity, and geometrically convex domain have like very strong rigidity property symplectic. So in R2N, I want to say something like convex domains have very strong rigidity properties. And like the property which is conjecture. I won't talk much about that one, but it's just to say that on convex domain, all kind of normalized symplectic capacity coincide on all convex domain. And we know it's not true on non-convex domain. So it's kind of very strong rigidity properties. But the problem with geometric convexity is not a notion which is really symplectic. By that, I mean, it's not invariant by symplectic transformation. So like, I want to say that geometric convexity is not preserved by symplectic isomorphism or preserved by symplectic transformation. So, to convince ourselves of that, if we just take R2, the symplectic form is the area form, and so a symplectic transformation is just a diffeomorphism which preserves the area, and then you can of course send anything convex on something of the same area but not convex. So that's in this talk, I'm going to stick to R4. Yeah, in R4. So I'm going to denote by C4, that is the set of domains in R4 which are symplectomorphic to a convex domain. And so those are domains containing R4, symplectomorphic to a convex domain. So that was one way to get around convexity, is to say, well, geometric convexity is not preserved by symplectic transformation. Let's look at all convex domain and all their image by all possible symplectomorphisms. Certainly, but then given a non-convex domain in R4, is it in that set or not? Really hard to say. I don't really have criteria. And so there are various other notions. One, which I think is the most famous one by Hofer, Vysocki, and Sender in '98. Is that correct, Helmut? It's called dynamical convexity.
Yeah, that's correct.
Okay, thank you. And so dynamically convex is a condition on the boundary of the domain And well, if you assume the boundary is smooth, you have characteristic, and it's a condition on all closed characteristics. And that's a notion which is invariant on the symplectomorphism. So that's a clean notion, and I'm going to denote by D4 is the set of domains in R form which are dynamically convex. And they proved in the same paper, so here I'm of September 98, that in my language, that C4 is included in D4, but every convex domain is actually dynamically convex, so it was really a generalization of convexity. So let me just draw a picture. We have the set C4. We have the set D4. And there was a long-standing question, whereas do we have equality here? And it was proved recently that no, there exists an element in D4 which is not in C4. That's a theorem by Chaidez and Edtmair. I think it was published last year, 22, is that there exists an element, a dynamically convex set, which is not symplectomorphic to convex sets. So basically, there exists a point here. I've got it. This is Chaidez-Edtmair example. And then the question that we were interested in with Julien, Vinny, and June was, okay, we know those are not the same, but how far apart are those distances? Like, is any dynamically convex actually very close to a convex set? And then if kind of symplectic, you can do continuous extension, then it's very good, or not at all. Yeah, so the question was, how far can dynamically convex domains, how far can they be away from convexity? So when I say how far, I have to put kind of a notion of distance. So let me so the notion of distance, this one was introduced by Ostrover and Polterovich. And it's a symplectic analog of the Banach-Mazur distance between sets in R4, which I'm going to redefine it a bit later on. But it's called the coarse distance because it's kind of the coarsest distance you can imagine between, like, containing symplectic data that you can imagine between sets in R4. And it's defined as if you take two sets, U and V in R4, you define the coarse distance between U and V as the infimum of log lambda was positive such that 1 over lambda U symplectically embeds into V and V symplectically embeds into lambda U, where lambda times the domain is just dilation factor, right? So that's symmetrical. And then when you have two collections, let's take A and B, two collection of subset of R4, yeah, collections of subsets of R4, we can define the coarse, by definition, the coarse distance, and now I have to insist, from A to B, is, and I'm going to call it sigma AB. So this is the supremum over all U in A of the infimum over all V in B of the coarse distance between U and V. So this distance, I really say from A to B because it's not symmetrical. So sigma is not symmetric. And let me just draw a picture. If I have this set is B and I have A inside B, then if I look at the closest, if I take any element U in A, the coarse distance from any element B in A is how much I can approach the element in A by element in B. But since element in A are also in B, I can approach them with lambda being 1. And so the distance is 0 in that case. Yeah, so here I have sigma AB is 0, but kind of sigma BA, that can be large in the picture. If this would be like an isometric picture, it would kind of be given by this distance precisely. So that's not symmetrical. And it has a nice property is that if B is contained in B prime, then the distance from A to B prime is less or equal than the distance from A to B.
Didn't finish the sentence.
Oh, sorry, but sigma BA can be large. Thank you. And so our main theorem is we looked at the distance from dynamically convex to convex. So in other words, we looked at point here, how can we squeeze them like by two convex, and what is like the largest ratio we have to achieve. And for me, it was very surprising, but this is plus infinity. So basically we could build here a family of example whose distance grows. And so the rest of the talk is going to be try to describe the family which achieve like a distance arbitrarily large. Yes, you have.
Is C one of the example in your list, in your sequence?
C, no. So that's I was going to make a remark later, but for that distance, you can essentially view CE with a parameter as a deformation of an element here, and so it's very close to C4. Even if you tweak the parameter and try to get far, it's bound the distance by, I forgot the precise constant, but let's say the distance is less than 2, for instance, which it's quite good. So I have to now let me, rest of the talk is given a family of dynamically convex domain, which get further and further from the set of convex domain. And why are they further? What are the tools we use to control the distance? So I'm gonna add two more sets to that picture, which are gonna be useful. So those are gonna be what's called toric domains. So a toric domain x omega in Cn or R to n is a set of the form pre-image by the moment map of a domain in the first orthon, so the pre-image of omega, where omega is in the first orthon of Rn, and the map mu is the map from Cn to this first orthon, which is the periodic moment map, so it sends Z1, Zn to pi times module of Z1 squared up to pi times module of Zn squared. So an example of such a thing is if we go back to n equal 2, and I look at the first quadrant and I look at pre-image of the triangle whose intersect with the axes are A and B. This corresponds to the set of Z1, Z2, and C2, such that pi module of Z1 squared over A plus pi module of Z2 squared over B is less or equal than 1. In other words, this is the complex ellipsoid of size AB. So I'm going to denote by T4 the set of toric domains, or the set of domains in R4 which are symplectomorphic to a toric domain. That's what I so I wrote toric domains, but I wrote, of course, the set of all the image and the symplectomorphic thing. So we have in this picture something like here. That is T4. Orange. Here in the set, it's toric domain, and they are, of course, convex. I have here somehow the set of all ellipsoids. So E4 is the set of all domains which are symplectomorphic to an ellipsoid of the type EAB. So E4 is the set of, I want to call them symplectic ellipsoid. So again, it's a set of all possible EAB and all their image and all possible symplectomorphism. And I have still one more set to add to that picture. It's a special type of toric domain, which are called monotone toric domain. So that was introduced by myself, V.Ramos, and Michael Hutchings. So a toric domain x omega is monotone if for all x in the, if you look at the moment map image in the boundary, so all x in, I want to call this d plus omega. So this is the boundary of omega intersect with 0 infinity n. So if at every point of this boundary, the normal vector at that point to the moment map image has all its components non-negative. So if for all x, the normal vector to omega at x, this is my point, x has all components non-negative. Now, we introduced this special class because I told you at the beginning that convexity, one of the things that was really interesting for me was this strong Viterbo conjecture. And we could prove that on all those domains, the strong Viterbo conjecture holds true, so that all capacity coincide on those type of domains. So they were really related to that kind of this convexity question. So it was Theorem by myself, Hutchings, and Vinny. Is like all normalized capacities coincide on monotone toric domain. So that was our main interest, and to relate it to the picture, we proved as a lemma that this monotone thing was a geometrical interpretation of dynamical convexity, in the sense that the toric domain is dynamically convex if and only if it is monotone. So, I forgot. I want to say that if I denote by M4 is the set of monotone toric domains, then we have M4 is equal to the intersection of T4 and D4. So in my picture, like this is okay. Now there's lots of sets in this picture, but maybe I'll go a bit back on this picture. I know you might wonder, I drew it like this, but are they the same or not? Kind of yes. So here we built with J.Dardennes and J.Zhang, so myself, J.Dardennes and J.Zhang, we built a family of examples of toric domain, monotone toric domain, which are not symplectomorphic to convex, using the criterion that Chaidez and Edtmair had created. There are, of course, elements here which are toric and very far from being dynamically convex. Those are all examples, that's like a family of examples due to Hermann. And Hutchings recently announced that he has found an element here, which is convex, but not symplectomorphic to anything toric. But I still haven't seen his draft, but he announced it in a conference in LB. Hutchings. And so now to go back to our main theorem, the main theorem is that the distance between D4 and C4 is plus infinity, meaning that this sigma is, I have to find the family of domain here in D4, such that if I want to kind of sandwich them by convex domain, I have to take a dilation factor very large. Yeah, and the family we're going to build is in this monotone toric. So the family is going to be something here. So the picture is not correct. I think there should be a direction going. So without further ado, let me just say what is the family. So the family of domain is parameterized by an element in between 0 and 1. And it's kind of, as p goes to 0, it will get further and further away. And so those are monotone torics, so I'm going to call them x omega p, and those are going to be the set of z1, z2 in C2, such that phi z1 squared to the p plus phi z2 squared to the p is less than 1. So it's kind of the symplectic LP ball. So the image by the moment map is something like this. That's okay. I was very surprised that those domain gets extremely far from being symplectomorphic. So the ingredient to prove that they are now far from all domains which are symplectomorphic to a convex domain is actually an old theorem from the 40s, which is called Yohn ellipsoid theorem. I think it's called Yohn because he was German. But...
I always call him John.
Indeed, Helmut.
Helmut is the German speaking.
Yeah, well, the Americans say John, I think. But John, but I think John would presumably what the Germans would have said.
So the Yohn ellipsoid theorem, it's basically the distance. It concerns the distance from convex sets to a set of ellipsoids. Here, not symplectomorphic. It was really old school geometry, and here it's about this Banach-Mazur distance. So the Banach-Mazur distance, if you take two sets UV in Rn, the Banach-Mazur distance between U and V is very similar to what I wrote earlier. So it's the infimum of log lambda such that there exists an element A in GLN and 2 points in Rn, such that 1 over lambda of translation of the domain U is included in the image of V by A, I mean V up to translation, which is itself included in lambda times U plus U. And if I denote by Ln the set of ellipsoids in Rn, and now I don't mean those type of ellipsoids, I mean really all real ellipsoids. Then the theorem from Yohn was published in 1948 is that for all convex sets in Rn, convex in Rn, we have that the Banach-Mazur distance between U and the set of ellipsoid. So this is the infimum, of course, over all ellipsoid of the Banach-Mazur distance from U to E. This is less or equal than 1/2 log n. So it gives really a kind of a characterization of being convex within distance to ellipsoid. That's why people are interested in that. And proposition, one of the first things we did was translate that Yohn theorem into in our symplectic world. And this translates into saying this sigma between C4, like from convex to ellipsoid. So if I want to take, it's again, sigma is take a convex set and you want to sandwich between an ellipsoid and its dilate and see how like small you can go, and then you should take the maximum over all convex set. This is less than log 2. This might not be an optimal bound. It's just the bound coming from Yohn theorem. And we know that Yohn theorem, that bound was optimal. There's example like a cube and a simplex, which achieve precisely that bound. If we take the cube and the simplex, we know we can get a lower bound, but that's it. For general thing, we don't, but it's a bound. Maybe let me do a slight digression and do a remark. Is the set E4 of ellipsoid is contained in the set of monotone toric domain. So sigma of from convex to monotone toric domain. So here is you want to sandwich convex domain by ellipsoid, and now you increase your set by taking all monotone toric domain. So of course, we know that this is less than log 2, but the conjecture is that this distance is actually 0. So that if you take any convex set, I can find a sequence of monotone toric domain which sandwich it, like we can basically approximate it better. I'm very fond of this conjecture because if you prove this conjecture, it's kind of a proof of the strong Viterbo conjecture for free. So it has strong consequences.
Wait, isn't this contradict? I don't understand how it aligns with the Hutchings example that you mentioned.
So this is something which is convex, not symplectomorphic to a monotone. Here I'm trying to pinch, and symplectomorphic and being pitch it's a weaker notion.
I mean, it's possible that his example would be a counterexample.
It's possible. We just don't know. It's pretty hard to compute those distances. But
so what's your philosophy here for that conjecture?
Oh, so it's kind of, if you take, let me get into the camera view. If you take any convex set, you can, like, by Joan, basically you include an ellipsoid and take basically square 2 times the ellipsoid and it's outside. Now you can try to push the ellipsoid gently in all the things you haven't filled the domain, and you can kind of squeeze outside, and that's, I mean,
Presumably the proof is a little bit more difficult. Yeah?
the proof is a lot more difficult, and the ideas I had to approach that problem are not at all by pushing or doing Ritchie flow on an ellipsoid. They are,
Because you will break them on towards
yes. So yeah, things are okay. I can talk more about that, but it's kind of filling boxes and packing things with boxes. But I can be more precise. Okay, now let me get back to the main theorem. So the main theorem was still that the distance from dynamically convex to convex is plus infinity. So I have to prove that this family gets further and further away from all convex sets. And I can say one of the first main ingredients is the triangular inequality. I mean that the coarse distance from one of my domain x omega p to the set of ellipsoid is bounded above by the coarse distance from x omega p to the set of convex plus sigma c4 e4. And by like the symplectic Young theorem, this is bounded above by log 2. So if we prove that this one is unbounded, we have that the one which interests us is unbounded. So it's again, we don't look at, like, we have this for family, we don't look at the distance for any convex, but we just take of the set E4, which is kind of big in C4. That's the philosophy. Okay, and now, like, the technical statement of the theorem is, I should put it D, G, R, Z, is that if P is less than 1/5, then the coarse distance from our domain x omega p to E4 to the set of ellipsoid is bounded below by 1/8 times log of, let me put a function g of p over 1 plus log 4 plus log of g of p, where g of p, this function, is 2 to the 2 over p minus 2 times the gamma function of 1 plus 1 over p squared divided by the gamma function of 1 plus 2 over p. Super nice bounds. No, horrible. So this part is actually the volume of this people. That's how it came about. This is like the volume in our form of x omega p. Okay, great. Now, we were very happy when we had that, because now we have, I mean, it's not pretty, but we have an explicit expression of this g of p, so you can asymptotically study how it behaves, and g of p tends to plus infinity, so quantity over there gets to plus infinity, which is exactly what we want. Yeah? So the remark, sorry?
I said painfully slow.
Yes, it grows painfully slowly, but it's like g of p goes to plus infinity as p goes to 0. To 0. Yeah, so that's, and there's a corollary which I also quite enjoy is we know that the distance from convex set or all set that are symplectomorphic to a convex domain to the set of ellipsoid is less than log 2. So as soon as the distance, the coarse distance from x omega p to the set of ellipsoid is larger than log 2, x omega p cannot be symplectomorphic to any convex domain. So this gives a new criterion of detecting some domains which are not symplectomorphic to a convex domain. So it's like whenever p is such that this distance is larger than log 2, so if I translate a little bit such that g of p divided by 1 plus log 4 plus log g of p, if this is larger than, that's 1/8, so it's 2 to the 8, so it's larger than 256, we have that x omega p cannot be symplectomorphic to any convex domain. Now, I mean, we had an expression, so we run it through a computer, and we made bets about starting at which p are we like really not convex, and the question was at which p or expression. And so in particular, let me put computer. This is true for all p less or equal than 1 over 62,460,059. Needless to say, this is of course not optimal, but the nice thing is it at least produced like a bound. It's not only an asymptotic result, it's a for all p less than, okay, here stupid small constant, all of those, I erased it, but all of those x omega p domain are not symplectomorphic to a convex. They are all dynamically convex, but not symplectomorphic to convex. So it gives also, a lot more examples. Yeah. Now,
so why is that 1 over 5 dash? The p less than 1 over 5?
it's kind of because of how we get the bound, we needed p to be low enough. Those are not fine bounds. Those are pretty crude bound, but they are the nicest bound we could make. I mean, sorry, it's not a, I don't think it's not a deep mathematical reason. It's like, for now, it's a purely technical reason. Let me maybe not say much about the proof, except that it's kind of complicated because you take one of those, you fix a p, you have one domain, and then you have to check the distance to all ellipsoid. Like to get the distance from one ellipsoid is fine, but then you have to vary a and b. And one of the nice things is in 4 dimension from ellipsoid to this p-ball, you have ECH, which helps you a lot. So proof, one of the ingredients is clearly ECH capacities. And somehow you, for each like for EAB, you find the case capacity which gonna really get the obstruction going. And kind of when you change A and B, you can kind of keep track of K, but then you change P. You take another one on the list, and then nothing tells you that the case capacity is going to be again the obstructions. You have again to check for it. So it's that's why we have like this crude bound and we cannot get better. So there's the ECH capacity. Another thing is, well, quite nice, but it's a volume obstruction. And then there's one thing which I want to call, let me call it a clever truncation. I call it clever because it was Vinny who saw it, so it's I'm not sending too many flowers to myself. It's clever truncation of the domain. And really entering the detail of how you get those ECH capacity and the ECH. Those are the ingredients. And I'm not gonna enter that much into technicalities. I just want to say a thing that was surprising for me is if I take back this LP ball, so this X omega P, at first it was really hard to get the distance. So the idea was, why not linearize the profile? Why not just take this domain? So I mean, this point is the point 2 to the minus 1 over P, 2 to the minus 1 over P. If that is, that's my domain. Omega P. And I thought, oh, this would be like nice approximation. Maybe we could say something, except it's a very bad approximation because there it's easier to compute what is the distance to this linearized red thing to the set of ellipsoid. And for all P between 0 and 1, we have that the coarse distance between X omega P, I want to call it linearized. Linearized, and the set of ellipsoid is bounded above by 1/2 log 3. So the linear things are actually very close to ellipsoids, and you need really to get the curve. So I have to admit that we didn't start by trying to prove the theorem that we could find dynamically convex, getting further and further away from convex. We tried to actually prove that that distance was bounded above by, and we were betting number below 10. And how things can. And just to, if you want to see this 1/2 log 3, is just to do a quick picture proof, is if you take this domain, you can symplectically embed it into, so this is the point 2 to the minus 1 over P, and now I take twice 2 to the minus 1 over P, up to 1. You can embed into that rectangle, and the image looks basically like something like this. You can kind of fold it. And now you have this symplectic embedding, and now you have to squeeze by ellipsoid. So here, with this curve, there's like a very natural ellipsoid inside. And now you have this rectangle up to 1, and you have this, and you just take the ellipsoid which contains that, and you can prove that the dilation factor is less than 3, so it's valid. And maybe part of an explanation for this, we could have guessed maybe that our approximation was bad, is that if you look at the volume of the approximation, so of X omega P lin divided by the volume of the original domain, this X omega P, this goes to plus infinity as P goes to 0. So they're actually a pretty poor approximation of the LP ball. And yes, and so as I was saying, this domain is at bounded distance, and it's a parameter of perturbation. So you can, by changing this parameter, you can get up as close as you want from C4. Same for all this family of examples. We can prove that those examples, there's a parameter, and if you take the parameter going to 0, you also get a distance 0 from the set of C4. So that family is kind of a new phenomenon, a new family of example that you can do as answering another old question. I'm not answering, but giving some light. Is if I look at the set of star-shaped domain in R4 with the coarse distance, let me denote that by S4 DC. This is a pseudo-metric space. And I don't know who phrased this question first. It was Leonid Polterovich was the one asking me the question, is in that space, how many linearly independent direction there is that goes to plus infinity? Like basically how you want to isometrically embed Rk in that, and what k, how k bit can be. So how many linearly independent directions in S4 DC? How many that goes to plus infinity? And that's called the rank of the matrix. And we have E4, which is in this S4. This gives at least 2 directions. Then we have those example by Hermann, 2 directions. So then we have this example, I want to say, Hermann, it's called one finger, because those are toric domain whose moment map image look like this, like a spike. And it's fairly easy to show that that's very far from the set of ellipsoid, and the further the spike goes, the further you get from all ellipsoid. So this gives us a 3rd direction. And I would say now this family X omega p gives the 4th direction. That's where we are now. The conjecture is that there's infinitely many, but we only have 4. So yeah, I think I'll stop here.
Questions?
So what is the important feature of this function? Is the value of omega p? It has to be very.
So kind of, yes, it's very tangent to the axis for basically a long time. That's the, I mean, okay, that's a waving hand example, but it's kind of the key feature. Is that if you, as soon as you want to put any ellipsoid inside, the ellipsoid has to be very tiny because it has no room to enter the spikes.
So is the condition any local, or do you also have like to control the rate of growth? I don't know.
Oh, you want like a general feature of the curve? That's we were very happy to find like one.
Yeah, just to get a sense of the geometric properties.
So we wanted to be monotone. So that was one thing. I would say the important thing would be on the axis to be very tangent. And okay, here you have to control, but I'm quite confident to say that if you want to perturb slightly the curve, that would still be fine, staying monotone. You would not change the result.
One feature that maybe I could say that this family has is if you look at the ball packing, up to a finite number of balls, like for whatever number you decide, that the volume of that relative to the volume of the whole thing goes to zero. SP goes to zero. So yeah, so like in like philosophically, you know, like ECH, like, you know, concave domains into convex domains, you know, you keep toric domains, that you can have these embedding if and only if the ECH capacities provide an obstruction, and then they only kind of look at a finite number of balls. So I think this philosophically has some.
Yeah, that's what all this truncation means. Yes.
I'm sorry, I think this is probably a naive question, but do you anticipate there's some sort of analog of these results to higher dimension?
I wish. So we think that it's, if you take the analog of, instead of the curve taking of like the smooth LP surface, we imagine it's true, but we crucially use that in 4 dimension. We have ECH capacity, which gets like necessary and sufficient condition for embedding some of the cases, which we don't have in higher dimension. And the capacities we have in a higher dimension are like not fine enough to get the obstruction.
Is it known that the C10 and DN are different in higher dimension?
Yes.
Already knew it was. There were examples like CE example.
Yes. The C example generalizes to higher dimension.
Oh, it does.
They did generalize it to higher dimension. And sadly, this picture is true in dimension 4. So, I mean, if you look at TM, it's still exact, but monotone toric might not be exactly the intersection of T4 and D4. You might have dynamically, no, they might, which, no, it's like, yes, you might have dynamically convex, which are not monotone. Toric dynamically convex, not monotone. That's what was really, we found some examples. So that picture is.
What is the systolic ratios of omega P?
Sorry, I'm coming back. This does not generalize to high dimension. Those generalize, but Chaidez and Edtmair generalize our example to high dimension. Sorry, good. Sorry.
Yeah, so how does the systolic ratios behave with P when for omega P and for the
I would have to compute. So this is, that point is precisely where the systole is. I'm ashamed because I computed, of course, 10 million times and I never remember.
I could probably compute myself. I just wondered.
Putting a lot of pressure on class. No, but so your office is right.
No, I would have to look in my notes.
Because since they're not like an ellipsoid far from long, say that basically an asking.
Oh, you go to
They go to.
It goes to zero.
It goes to zero.
That's what I would imagine. Yeah. You think it goes to zero?
Yeah, no, it goes to zero. Yes, but I don't know the precise.
Yeah, that's fine. I
But
just
yes, they
wanted to know.
both go to zero.
Like, yeah.
Yeah. So maybe I took a bit.
Any more questions?
Yeah, I have a question. So when you use a John ellipsoid to approximate, say, from the inside, does one, or any ellipsoid, can one sort of, then the ellipsoid has this 2 minimal periodic orbits in the generic case, and do we know how close are they to periodic, or can they be embedded in such a way that they are close to periodic orbits on the convex set actually? it doesn't know anything about that.
No, so oh, sorry.
So for example, these two guys are a Hopf link. And on the convex set, presumably there's a Hopf link as well as for periodic orbits. Can I approximate that also in this? Is there some kind of John theorem which approximates this in addition?
I don't know. I never succeed in anything. I was even trying to say that you have an ellipsoid, even kind of assuming the first embedding is very nice, and kind of is the
Hello? Okay, you were cutting out, so it must have been very deep. So,
oh.
So I heard is, so I only heard the very, very beginning from what you said. So maybe you should repeat it.
Yes, I was saying you have your convex set. My picture is not convex. And I was saying here you can put maybe a nice ellipsoid in here. And in the ellipsoid you have, even just take the short periodic orbit on the ellipsoid. And I was saying, will a neighborhood of that orbit touches the convex set? Or if you take the other orbit, will they touch? Yeah. And in that neighborhood be an orbit, and I could never get anything there. Now, even to say I have two orbits, I control their actions. Is the periodic orbit of action very close? Well, the squeezing tells you that capacities view period of periodic orbit. So yes, there are periodic of action in a window not too far from those of the ellipsoid, and by not too far, by the distance give you the squeezing, but I cannot say much more, sadly. Mm-hmm. It's not satisfactory.
Are there examples that you get exactly, like I would imagine if you take, I don't know, a cube, and then you take the John ellipsoid of the cube, then you probably show that they have to be on like distance, like, I don't know, maybe maximalized or almost maximized. Between the shortest periodic orbits of the ellipsoid.
So if you take a cube, cube is symplectomorphic to a polydisk, P11, and you can embed E12 right in, so in complicated way.
Yeah.
So here you have orbits of one, and
I see.
And then you can put like a dilate of E12. You have to take the correct dilation, which is pass, and that gives you the bound for the distance. But kind of.
Is it going to be the? Wait, if you take the dilation of that now, that contains.
Yes, you have to contain 1,1.
Yeah. So doesn't it mean that the periodic orbit will be big over there? So like one of the ellipsoids, either the interior or the outer ellipsoids, is going to have a different minimal, like a far minimal period than the cube, right?
No, it's completely correct, because kind of for ellipsoid, the small orbits, all orbits are symplectic capacities. So if the interior and exterior one for the same capacity were very close, it would say the sandwich is super close to the cube, which we don't have.
I see.
And, I was saying the other way, that if you have a distance, yes, the one of them can be close, and
you don't know if it always happens that one of them is close.
But my guess is yes, that's the kind of, if you take the optimal ellipsoid, which approximating, the smallest orbit is well approximated by either inner or outer, but that's just a wild guess. All examples work. That's it. Okay.
Any more questions? All right, now let's take it again.